Okay, welcome back, and today we're going to start the next phase, or well, topic for the two population testing. So this is now, last time we talked about the two populations, so testing for population means for two populations, seeing if there's a difference between means. So for the hypothesis test for the difference of means, we assumed that we knew the population variances or the population standard deviations. Now what we're going to do is, what if we don't know either one or both of them? Okay, so we're not going to be able to use the normal distribution, and so what we're going to do is, instead of sigma, we're going to replace them with S, right? So we're going to use the sample standard deviation, and then of course, instead of a normal distribution, we're going to end up having a t distribution. So it's going to be very similar to what we did before. So whenever we don't know the standard deviations for the populations, we're going to end up using the t distribution again. Okay. So now here's the thing. So here's the statistics. So the test statistics. So keep in mind that everything else is the same, right? Except we're going to use the standard error of the estimate instead of the standard deviation because we don't know sigma. So the standard error is going to be equal to this. So all we're going to do is replace the denominator from our, or actually, you know what, let's do this. Well, yeah, let me just read this. So instead of using what we did before, where we had sigma 1 squared over n1 plus sigma 2 squared over n2, we're going to now replace those with s. So it's going to be s1 squared over n1 plus s2 squared over n2. And so that's going to be the standard error because we don't know sigma 1 or sigma 2. So we're going to replace those with s1 and s2, and that's the only difference. Plus, it's going to be a t distribution, obviously. Okay? So in this regard, our test statistic is going to be a t star again. But in this case here, again, everything else is going to stay the same. So it's going to be x bar 1 minus x bar 2 minus mu 1 minus mu 2 divided by, again, the standard error, which now is going to be s1 squared over n1 plus s2 squared over n2. So that's going to be our test statistic for t star in the case where we want to test the difference between two population means. And again, under the null, this is going to be 0. So this is just going to be 0, so it's going to be reduced to x bar 1 minus x bar 2 divided by the standard error. And that's it. Okay? So now again, the only difference is we're going to be using the t distribution, so we're going to be using inverse t, CDF, and then instead of a two-sample Z test, we're going to end up doing the two-sample T test. Now, the other assumption too that we're going to make is not only do we not know the standard deviations, but we're also not going to assume that they're equal for the time being. Okay, so we're going to assume the population variances are not the same. Okay, so in that case, this is going to be our standard error, but the degrees of freedom, right? With the t distribution, we have to know the degrees of freedom. Well, the degrees of freedom, when we're dealing with difference of means and we're dealing with adding the variances and taking the square root, or actually adding the standard errors and taking the square root of the sum of the standard errors, it gets to be a pretty complicated formula. So with the t distribution, when we don't, and again, we're assuming, right, we're assuming that sigma 1 squared is not equal to sigma 2. So we're not going to assume that they're the same. We don't know them, right? So the sigma 1 and sigma 2 are unknown. Okay? So Okay, yeah. So they're not equal. I just wanted to make sure I wasn't writing off the board so you guys couldn't see. But sigma 1 is not equal to sigma 2. Okay, so that's our assumption. We're not assuming that. And in that case, this is the calculation that we would need to use for the test statistic. And the degrees of freedom calculation is a pretty complicated one. Okay, and that complication, formula is this. Okay, it's going to be S1 squared over N1 plus S2 squared over N2. And we're going to take that quantity and square it. And then we're going to divide that by this, which is going to be S1 to the fourth divided by N1 squared times N1 minus 1 plus S2 to the fourth over N2 squared over N2 minus 1. Okay, so that's one variation. Okay. I've seen it where the denominators are written a little bit differently, but obviously this is a complicated formula. Okay. And you don't always get a whole number value for the degrees of freedom. Most of the time you'll get some value with decimals. But the thing is, you don't have to worry about calculating this by hand because your calculator will actually calculate this for you. Okay, so you don't need to know the degrees of freedom because we're going to use the calculator. Okay, we're not going to use the table. Okay, now the other way I've seen this, just so you know, is this. Okay, I'm just going to change the denominator a little bit. Okay, so I've also seen it this way. S1 squared over N1 quantity squared times 1 over N1 minus 1. Okay, and then I can also rewrite this one the same way. Okay, and so I've also seen it this way. So it's going to be 1 over N2 minus 1 times S2 squared over N1 quantity squared. So again, that's another way of writing it. Same thing, same formula. But anyway, this is not what we're going to be doing. Okay? But I wanted to show you this so that you understand how to calculate the t statistic for the test. Okay? Now, what we're going to use is instead of this, we're going to use the calculator. And like I said, we're going to use the 2-SAMP t-test. Okay. Now here's the thing. Again, it's going to ask you for certain things for the test. It's going to ask you for what is S1, what's S2, what's X bar 1, X bar 2, N1, N2. It's also going to ask you for the alternative hypothesis. So you're going to have to put in either greater than, less than, or not equal to, right? Okay, one of these three. But also it's going to ask you whether you want to pool, whether you're pooling the samples or not. And what does that mean? Pooling, if you remember from before, did it come up in confidence intervals? Not sure. But anyway, pooling has to do with the assumption of this, of whether we're going to assume that the population variances are equal or not. Are they the same? Okay. If we assume that the population variances for both populations are the same, then what we can do is we can take the samples and pool the samples together and come up with a pooled variance, like pooling the variances together so that we use a common variance or a variance for the common sample, okay, if that makes any sense, okay? But the question here is going to be pooling is going to be yes or no, okay? If we're going to assume the population variances are the same, then yes, we're going to pool the samples, okay? But if we're assuming that they're not the same, then we don't pool. So the answer would be no. So in this case here that I just went through, that's under the assumption that we're not going to pool, okay? Or the assumption that the variances are not equal, okay? So we are not going to assume that the variances are equal for right now, okay? Okay, now, so in that case we would say no, and then it'll calculate the correct t statistic and the correct degrees of freedom, okay? In a moment, we'll talk about what happens if they are equal. What happens if we can assume that the variances are equal even though we don't know what they are, okay? We'll get to that in a moment. But right now, we're going to assume that the variances are not equal and the variances are unknown. And the key is if they're unknown, we're going to do a t distribution with the t statistic that I just went through, okay? So let's do an example. So now, let's see here. So let's say for this example says, let me just make sure here. Okay, I just want to make sure. Okay, good. Okay, so now let's use this example. So it says the average amount of time boys and girls aged 7 to 11 spend playing sports each day is thought to be the same. A study is done and data are collected, resulting in the data in the table below. Each population has a normal distribution. So again, we have normal populations, independent samples, and so we're good there, okay? So now the thing is they give us data, okay? They give us the sample size for each one, which turns out to be small sample size. The number of girls is 9, the number of boys is 16. So again, we have small samples. So, but we are still given that the populations of boys and the population for time that boys spend playing sports each day and the population of time that girls spend playing sports each day are both normally distributed. Now, what they don't give us is the population standard deviations for each, okay? We don't know those. But they give us the sample standard deviations and the sample mean. So we're going to use a t-distribution in this case. And it says using a significance level of 5%, is there a difference in the mean amount of time boys and girls aged 7 to 11 play sports each day? Well, let's figure that out. Let's find out. So now, we want to know if the average time that boys and girls spend playing sports every day is the same. Okay. Okay, so that's what they claim. So now, the claim here, the claim is that the average time that boys spend playing sports is equal to, right, is the same, the average time girls spend playing sports each day. So what do we get? Well, again, we have to determine which is going to be mu1, which one is going to be population 1, which is going to be population 2. And so let's just do this. Let's make this population 1, and let's make this population 2. Oops, rewrite that a little differently. So we'll say the population of boys is population 1, right? So average, so time the boys spend. So this is going to be population 1, population 2. And so what do we get? The average time for boys is going to be mu1 then. The average time for girls is mu2. And of course, we're going to set those equal. So that's the claim. So in other words, what do we have? We have the null hypothesis is going to be mu1 is equal to mu2, which is our claim in this case, versus the alternative, which is then going to be not equal to, right? So one of them is significantly different. So whether it's whichever direction it is, it doesn't matter. So it's going to be not equal to, mu1 is not equal to mu2. And so now, what do we got? We got a two-tailed test here, okay? So two-tailed. Okay, so now that's step 1, right? So now step 2 is, what are we going to do? We're going to assume the null is true. So we're going to assume there's no difference between mu1 and mu2. So again, so we're going to assume mu1 is equal to mu2, or in other words, we can rewrite it this way. mu1 minus mu2 is equal to 0, right? So now step 3 is we're going to write down the information. So the alpha level, again, is 0.05. Again, it's not always going to be that. And so what do we have? We have this table. So let's write down the table here. Okay. And so what do we have? We have, let me extend this out. Okay, so we have this table. So here's girls, and here's boys, and here's the sample size. So here's N, X bar, and S. Okay, so for the boys is population 1. So N1 equals 16. N2 equals 9. And then X bar 2 equals 2. And X bar 1 equals 3.2. And then S1 equals 0.873. So 0.873. And then S2 equals 1.0. Okay, so that's the data. Now, the fact that we don't know sigma, so we're, again, sigma 1 and sigma 2 are unknown. Okay, something important to note. Now, also, they don't tell us anything about the population standard deviations as far as we should assume that they're equal or not. So the rule of thumb is, when in doubt, don't pool. So when in doubt, we're going to assume that they're not the same. Okay? So unless it's obvious that they should be the same, for example, if these two standard deviations here were the same, then that would be reason to assume that the population variances are also the same. Okay? But these two are not the same. So again, and also, if it says in the problem, assume that the population variances are the same, then obviously, then we would do so and we would pool. But in this case, since they don't say anything, and the sample standard deviations are not the same, then we're not going to assume they're the same. So we're going to assume, so again, when in doubt, assume that they're not the same. So we're going to assume that sigma 1 squared is not equal to sigma 2 squared. Okay? And so that means we're not going to pool, right? So that means no pooling. Okay. So now we know we're going to use a t-distribution. So now here again, step 4, we could calculate our t statistic, right, by using our formula, which is what? It's going to be x bar 1 minus x bar 2 minus mu 1 minus mu 2 over the standard error for both populations. So it's going to be S1 squared over N1 plus S2 squared over N2, and then take the square root of the sum. Okay? And so again, this becomes 0 because under the null, we're assuming the difference is 0. So this difference becomes 0, and all we have is this. And of course, if we plug in chug, what do we get? Let's find out. Okay, so what do we do? So let's put in, so x bar 1 minus x bar 2. So remember, you make sure you subtract them in the right order. 3.2 minus 2, so that's going to be 1.2. Divided by the square root of S1, oops, oh, I got these mixed up, I'm sorry. Hold on. This is S2, right? I got these backwards, sorry. S1 is 1, S2 is 0.873, right? So these got to match up, okay? The numbers are in the right order. I just accidentally switched those. Okay, good. So N1, X bar 1, S1, N2, X bar 2, S2. Okay, and we're doing boys, right? Boys was population 1, so that's good. Okay, so we got everything right. So now I'm going to put in this squared over this n. So I'm going to do S1 squared over N1. So it's going to be, so 1 divided by 16 plus, and then it'll be 0.873 squared divided by 9. And I get 3.128. 3.128. Okay. Pretty big. Okay. Now, I could use this and use the traditional method, or I could then go forward and find the p-value. So the p-value here would equal the probability, since it's a two-tailed test, I'm going to find the probability of being bigger than this, right? Equal to or bigger than this, and then double that probability because it's a two-tailed test. Remember, I have an area in both tails that I have to add together. So in this case, it's a two-tailed test. So I'm going to find the probability of being that my t star value is greater than or equal to 3.128. And so in order to find that probability, I'm going to use TCDF. So TCDF, and now my lower bound is going to be 3.218. It's greater than or equal to, right? So 3.128 to then 10 to the 99th power is my upper bound. And then the degrees of freedom, oh, I don't know the degrees of freedom. I have to do that crazy calculation. Okay, well, I'm not going to do that calculation. So here's what we're going to do. Here's the rule of thumb that you can use. Typically, instead of using that calculation, what we will do is we'll use the degrees of freedom of the smaller sample. And we'll use that as a conservative estimate. Okay? So what we'll do is we'll take the larger sample. Did I say smaller? It should be the larger sample. Hold on. Is it the smaller? Oh, I gotta look. No, it's a small. I believe it's the smaller. Yep. Yeah. You take the smaller degrees of freedom. So you take the minimum value. That's what it was. You take the minimum value to be more conservative. So in this case here, we're going to take the sample size 9, and we'll use degrees of freedom 8, and we'll use that as a minimum value. Okay, when we get to the calculator, I'll tell you what the degrees of freedom actually turn out to be, but typically we'll use the minimum value. Again, it's just a rule of thumb. So we'll see what we get. So, because I don't want to calculate it out. Okay, so let's do that. So TCDF, let's go to our distribution. So TCDF, and we're going to use 3.128, comma, 10 to the 99th power, comma, and then the degrees of freedom we'll just put in 8. And what do we get? We get 0.0070. 0.0070. And then now we can use this as our p-value. We could use this as our t star, so we can use the traditional method or the p-value method to get the conclusion. And of course, whichever one you use, we're going to end up doing what? Well, alpha is 0.05, so we're going to end up rejecting the alternative. We're going to end up rejecting the null hypothesis. And so basically what we're going to do, we're going to reject the null hypothesis, which is the claim. So in this case, our conclusion would be at an alpha level of 0.05, there is strong evidence to reject the claim that the average time that boys spend with playing sports every day is not the same, or should it, to reject the claim that the average amount of time boys spend playing sports every day is the same average time that girls spend playing sports every day. Okay, so we're going to reject that claim. Okay, so now let's go back, and now what we're going to use is we're going to use two sample t-test, right? And so in the two sample t-test, and it's under stat calc or stat tests. So let's go to the two sample t-test. And now we're using statistics, right? They're giving us the statistics. We don't have data. So we're going to choose the stat option for input. Now it's going to ask me for x bar 1. Well, x bar 1 is 3.2. And then S1 is 1. N1 is 16. X bar 2 is 2. S2 is 0.873. And N2 is 9. And now the alternative hypothesis we're using is not equals. And now it asks me, am I pooling the samples or not pooling the samples? Well, no, we're not pooling the samples. So we're going to choose no. And now calculate. And we get a t statistic. T star is equal to 3.128, exactly what we got with our calculation, the formula. Okay, now let's look at the p-value. So p-value is equal to 0.0056. So a little bit different. Why is that? Well, the degrees of freedom turns out to be 18.726. So approximately 18.7. Okay, it just goes on and on. So that's the degrees of freedom. Why? Because we're not pooling the data, so the degrees of freedom is calculated using that very complicated looking formula that I showed earlier. Okay, so now this is what we get. But again, remember, if you use the minimum value in the calculator, you'll still get the correct answer. Okay, so now step 5, of course, is the comparison. So whether you use this or this, you can get the critical value for the t. So the critical value for the t, remember, we're going to use the degrees of freedom, or excuse me, I'm sorry, we use alpha, right? So we're going to use the area to the left, so I'm just going to calculate, I'm just going to see what it is. I'm curious. So let's go to second vars. We're going to use inverse t, and the area to the left is going to be alpha divided by 2, right? It's a two-tailed test, so we've got to make sure that we use alpha divided by 2 in both tails. So that means the area to the left is not going to be the alpha, okay, or to the right, but it's going to be half of alpha in each tail. So that means the area to the left of my critical value, or yes, the area to the left of my critical value, and I have two critical values, right? So if I use the right-sided, the positive critical value, then the area to the right is going to be equal to alpha divided by 2, which is going to be 0.025, which means the area to the left is going to be 1 minus that, so it's going to be 0.975. And then what I'm going to do is I'm just going to use, again, the degrees of freedom, the minimum value. So I'm going to use 8. So I'm going to stick 8 in here. And I get 2.306. So I get T alpha divided by 2 is equal to 2.306. And so obviously my test statistic falls within the rejection region. And again, my p-value is definitely less than alpha. So again, both methods give you the same answer. And then so if I use the p-value method, so is equal to 0.0056, alpha is equal to 0.05, and so therefore, again, my p-value is less than alpha, so therefore, I reject the null. And so 7, again, at an alpha level of 0.05, there is very strong evidence to reject the claim that the average amount of time that boys and girls spend playing sports every day is the same, based on the sample data. And that's it, guys. So now let's do another example. So let's see what else we got. Let's see. Okay, let's see what we got. Give me 1 second. Okay, I want to just choose a good one here. Oh, let's see here. Let's do this one. So on this one, go faster since we've already done it once. I'm going to just run through it. Okay, So it says a study is done by a community group in 2 neighboring colleges to determine which school graduates students with more math classes. College A samples 11 graduates. The average for this sample is 4 math classes with a standard deviation of 1.5 math classes. College B samples 9 graduates. Their average is 3.5 math classes with a standard deviation of 1 math class. The community group believes that, on average, students who graduate from College A have taken more math classes than students from College B. Assume that both populations have a normal distribution, and we are testing at a 1% significance level. Okay, so that's what we want to do. So now, the claim is that College A has students graduating with more math classes than students from College B on average. Okay, so now, here's what I'm going to do. I'm going to make College B population 1. Let's do this. Oh, I'm just going to keep it the same. Let's say College A is population 1 and College B is population 2. So if the students on average are doing more math classes, taking more math classes on average at College B than College A than at College B, then it would be the mu1 greater than mu2, okay? So it's going to be this situation here. So mu1, so population 1 is College A, population 2 is College B, and we're saying that College 1, the average number of math classes at College A is greater than the average number of math classes that students take at College B. So in other words, we're claiming that mu1 is greater than mu2. So that's going to be versus mu1 is less than or equal to mu2, and the claim is the alternative. And it's a right-tailed test. Okay? So again, step 1. Step 2, we are going to assume that mu1 minus mu2 is equal to 0. Okay? No difference. So we're assuming the null is true, that mu1 is equal to mu2. Okay? So now 3, let's write down the information. Okay. Here's the way I'm going to write it down. So we have A, which is population 1, and we have B, which is population 2. So for A, N1 is 11 because they sampled 11 graduates. And the average X bar 1 for these 11 graduates was 4. And S, right, the standard deviation for these 11, S1, was equal to 1.5. Now for College B, N2 was equal to, what was it, 9. X bar 2 was equal to 3.5. And S2 was equal to 1. And so there's our data. Now, they don't say anything about the population standard deviations, so we don't know. So sigma 1 and sigma 2 unknown. They don't tell us if they're the same or not. So again, when in doubt, assume they're not equal. So we're going to assume, oops. So we're going to assume that x sigma 1 squared is not equal to sigma 2 squared. And if you look at the sample standard deviations, they're not the same either. So again, we're not going to do this, which means not pooled. Okay, so we're not pooling. Okay? Okay, that's it. Oh, by the way, alpha. We need our alpha level. What's the alpha level? This time it's 0.01, 1%. So our alpha level is 0.01. Can't forget that. Okay, so now let's go to step 4. And in step 4, we're going to use the t distribution. Oops. Which is the 2-sample t-test. 2-sample t-test. And so t star and p-value will come right directly to that. So I'm just going to go to the calculator. I'm not going to deal with doing the calculations again. So I'm just going to go straight to the test. So we're going to use stats again because we have the sample statistics. So we're going to use stats. And the x bar 1 is 4. S1 is 1.5. N1 is 11. X bar 2 is 3.5. S2 is 1. N2 is 9. And what is the alternative hypothesis? Greater than. It's a right-tailed test, so I'm going to go over and select greater than. And now I'm going to go down to pooled. No, we're not going to pool. And now calculate and look at that. Our t statistic. Ooh, look at this. Our t statistic is 0.889. If we round, it's going to be 890. 890. That's our test statistic. Okay, looks like a p-value, but it's not. It's our test statistic. Our p-value, on the other hand, is 0.1928. 0.1928. Large p-value. So now, let's do our comparison. Okay, so I'm going to use the p-value method since it's easy. So again, p-value equals 0.1928. Alpha is equal to 0.01 in this case. Is my p-value less than alpha? No. So now, what's the result? Therefore, we fail to reject the null hypothesis. And then 7 is the conclusion. So now, we fail to reject the null. So what does that mean for our claim? In this case, since the claim is the alternative, we would have to conclude that there is not enough evidence to support the claim. So at an alpha level of 0.01, there's not enough evidence to support the claim that what? That the average number of classes that a student takes at college A is greater than the students at college B, based on the sample data. And that's it. Okay, so next time, guys, we're going to do the same thing, but then we're going to do a couple of examples where, what if we do know that they're pooled? Okay, what if we do know that the standard deviations or the variances of the population are the same? Well, the only difference is we're going to use pooled, and that's it. So when we come back next time, I'm going to do a couple examples of that, and I'll explain it quickly, and then we'll be done with these tests, and we'll move on to proportions. Okay? So thanks again, and I'll see you next time.